Welcome to my sleep science channel, where we slowly explore the mysteries of the universe together. Before we begin, please consider liking the video, subscribing to the channel, and sharing in the comments where you're watching from. Tonight, we begin a peaceful journey toward one of the most fascinating destinations in the cosmos, the Andromeda Galaxy. Long before telescopes became powerful enough to reveal the true scale of the universe, people looked into the night sky and wondered whether the faint glowing patches above were clouds, stars, or something entirely different. Among those mysterious objects was a small hazy shape located in the constellation of Andromeda. To the naked eye, under dark skies far from city lights, it appears as a dim blur, almost like a tiny cloud floating among the stars. For thousands of years, nobody knew what it really was. Today, we know that this faint object is not a cloud at all. It is an enormous spiral galaxy containing hundreds of billions of stars. Known as the Andromeda Galaxy, it is the nearest major galactic neighbor to our own Milky Way. In many ways, it resembles our home galaxy. It has spiral arms, vast regions of gas and dust, clusters of ancient stars, and likely countless planets orbiting countless suns. What makes Andromeda especially fascinating is that it is visible without any telescope. The light entering human eyes from this distant galaxy has traveled across space for approximately 2.5 million years, long before the first humans appeared on Earth, long before the construction of pyramids, long before ice ages came and went. Those photons had already begun their journey. Every time someone looks toward Andromeda, they are seeing ancient light that left its stars when completely different creatures roamed our planet. Although Andromeda appears small and gentle in the night sky, its true size is astonishing. It stretches across more than 200,000 light years and contains perhaps 1 trillion stars. Some scientists believe it may contain significantly more stars than the Milky Way itself. Within this vast island of suns are countless nebulae, star-forming regions, black holes, and planets that have never been seen directly. For centuries, astronomers debated the nature of these distant objects. Some believed they were small clouds located inside our own galaxy. Others suspected that they might be enormous systems far beyond the Milky Way. This debate continued until the early 20th century, when observations finally revealed the truth. The Andromeda Galaxy was not part of our galaxy. It was an entirely separate galaxy, unimaginably distant, existing as another great city of stars floating in the cosmic darkness. Suddenly, humanity's understanding of the universe changed forever. If Andromeda was another galaxy, then perhaps there were many more. As telescopes improved, astronomers discovered that the universe was filled with galaxies. Not dozens, not hundreds, but trillions. Each galaxy contains stars by the billions, and many of those stars likely possess planets of their own. The universe became far larger and far more mysterious than anyone had previously imagined. Despite this overwhelming scale, Andromeda remains special. It is our nearest giant neighbor. In a sense, it is the galaxy next door. While millions of light years separate us, it is close enough that gravity binds both galaxies together. In fact, measurements show that Andromeda is slowly moving toward the Milky Way. Over billions of years, the two galaxies will eventually merge into one enormous new galaxy, transforming the skies of future worlds. As we sit comfortably and imagine the stars above, it is remarkable to realize that the faint blur in the constellation of Andromeda is not simply another object in the sky. It is an entire universe of stars, planets, and mysteries. Somewhere within its immense spiral arms, there may be worlds illuminated by unfamiliar suns. There may be oceans beneath alien skies, mountains never climbed, and perhaps even forms of life that have spent millions of years wondering whether they are alone. Tonight, our journey begins with this simple realization. The Andromeda Galaxy is real. It exists at this very moment, quietly shining in the darkness. 2.5 million light years away, Between our galaxy and that distant spiral lies a vast ocean of space so immense that even light itself requires millions of years to cross it. Understanding that distance and asking how long it would actually take to travel there opens one of the most extraordinary questions humanity has ever imagined. When people first hear that Andromeda is our closest major galactic neighbor, the word neighbor can create a misleading impression. In everyday life, neighbors are close. They might live across the street, or perhaps in the next building. In the universe, however, the meaning of nearby becomes something entirely different. Even the closest giant galaxy is separated from us by a distance so enormous that ordinary numbers begin to lose their meaning. Modern measurements tell us that the Andromeda Galaxy is located approximately 2.5 million light-years away from Earth. This number sounds impressive, but it is difficult for the human mind to truly understand. Our brains evolved to navigate forests, mountains, and oceans, not the unimaginable dimensions of the cosmos. To appreciate this distance, it helps to begin with things that feel familiar. Imagine taking a walk through your neighborhood. Perhaps you travel 1 kilometer in 15 minutes. If you continued walking without ever stopping, day and night, year after year, it would take many years simply to cross a country. Crossing an ocean would require even more time. Yet these distances are tiny compared with the scale of our planet. Earth itself is about 40,000 kilometers around. Light, the fastest thing known in nature, can circle our planet more than 7 times in a single second. That same light requires about 1 second to travel from Earth to the Moon. The Moon, which appears so distant in the night sky, is actually very close on the cosmic scale. Traveling farther outward, sunlight requires roughly 8 minutes to reach Earth. The Sun is nearly 150 million kilometers away, a distance so vast that millions of Earths could fit inside it. Even this enormous separation represents only a tiny fraction of the dimensions of our own solar system. Beyond the planets lies a region filled with icy bodies and comets. Farther still exists the Oort cloud, a gigantic spherical shell of frozen objects surrounding our solar system. Some estimates suggest that light itself may require more than a year to cross from the Sun to the outer boundaries of this distant cloud. Already, the dimensions involved have become almost impossible to picture. Yet the journey to Andromeda extends far beyond the edges of our solar system. It stretches beyond neighboring stars, beyond giant clouds of gas and dust, beyond the spiral arms of the Milky Way itself. Our galaxy contains hundreds of billions of stars spread across roughly 100,000 light-years. Even traveling at the speed of light, crossing our own galaxy would require 100,000 years. Andromeda lies 25 times farther away than the diameter of the Milky Way. In other words, if our galaxy were reduced to the size of a dinner plate, Andromeda would still be located many meters away. Between the two galaxies lies an enormous region known as intergalactic space. Contrary to popular imagination, this region is not crowded with stars and planets. It is mostly empty, containing only sparse gas, invisible dark matter, and occasional wandering stars. Astronomers did not always know the true distance to Andromeda. In fact, until the early 20th century, many scientists believed it was simply a cloud located inside the Milky Way. Everything changed when observations made using powerful telescopes revealed certain stars whose brightness could be used as cosmic measuring tools. By studying these stars, astronomers discovered that Andromeda was far outside our galaxy. The universe suddenly became much larger than anyone had imagined. Today, more advanced techniques involving variable stars, supernova explosions, and detailed observations have refined those measurements. While slight uncertainties remain, scientists agree that Andromeda lies approximately 2.5 million light-years away. Light leaving the galaxy today will continue traveling through space for millions of years before finally arriving at Earth. This means that when we observe Andromeda, we are not seeing it as it exists right now. We are witnessing ancient history. The image reaching our telescopes tonight began its journey long before modern humans existed. Entire species have appeared and disappeared on Earth, while those photons traveled silently through the darkness between galaxies. Perhaps the most remarkable aspect of this immense separation is that Andromeda is actually approaching us. Gravity is slowly pulling the Milky Way and Andromeda toward each other. Although 2.5 million light-years sounds like an impossible gulf, the two galaxies are drifting together at hundreds of kilometers every second. Even at that tremendous speed, their encounter remains billions of years in the future. From a human perspective, 2.5 million light-years might as well be eternity. Civilizations rise and fall within thousands of years. Human history occupies only a tiny fraction of the time represented by the light currently reaching us from Andromeda. Yet the universe measures time and distance on scales far beyond human experience. Galaxies move patiently. Stars are born and die over millions and billions of years. Cosmic events unfold with extraordinary slowness. As we continue our quiet journey through the night, it becomes clear that the challenge of reaching Andromeda is not simply a question of building a powerful rocket. It is a question of understanding scales so immense that even the fastest things known in nature struggle to bridge them. The 2.5 million light-years separating our galaxy from Andromeda represent one of the greatest distances humanity can easily point to in the night sky. A reminder of both the vastness of the universe and the incredible journey that light itself undertakes to connect distant worlds. The distance between the Milky Way and the Andromeda Galaxy is so enormous that ordinary units quickly become useless. Kilometers work perfectly for measuring roads, cities, and even planets. But once astronomers began studying the universe beyond our solar system, they realized that familiar measurements could no longer describe reality in a practical way. Writing down the exact number of kilometers between Earth and Andromeda would require so many digits that the figure itself would become difficult to read and even harder to understand. Human beings have always measured distance according to the world immediately around them. Ancient civilizations used footsteps, ropes, and landmarks. Later, more precise systems emerged, allowing people to map continents and navigate oceans. These methods worked because Earth, despite its size, is still small enough to fit comfortably within human understanding. Space, however, introduced dimensions unlike anything encountered before. The moon, which appears close and familiar in the night sky, is nearly 400,000 kilometers away. A journey by modern passenger aircraft would take weeks. Light, traveling at nearly 300,000 kilometers every second, reaches the moon in just over 1 second. Even this comparison begins to reveal how different the scales of the universe truly are. The sun lies much farther away. Sunlight that warms Earth every day began its journey approximately 8 minutes earlier. In those 8 minutes, light crosses 150 million kilometers. That distance became the foundation for another useful unit, called the astronomical unit. 1 astronomical unit represents the average distance between Earth and the Sun. Within our solar system, astronomers often rely on this measurement because using millions and billions of kilometers repeatedly becomes inconvenient. Mercury orbits at less than 1 astronomical unit. Jupiter lies more than 5 astronomical units from the Sun. Neptune circles nearly 30 astronomical units away. Beyond the planets, the distances continue increasing. The icy objects that inhabit the outermost reaches of the solar system are separated by hundreds or even thousands of astronomical units. Despite these enormous numbers, the entire solar system remains only a tiny neighborhood compared with the vastness that stretches beyond. The nearest star to our Sun, Proxima Centauri, resides more than 4 light-years away. Suddenly, even astronomical units begin to lose their usefulness. This is where astronomers turn to one of the most famous measurements in science, the light year. A light year is not a measure of time, despite its name. It is a measure of distance. It represents the distance light travels in 1 year. Since light moves with incredible speed, nearly 300,000 kilometers every second, the distance covered in a single year becomes astonishingly large. 1 light year equals approximately 9.5 trillion kilometers. Even such gigantic numbers only begin to describe the universe. Proxima Centauri, our nearest stellar neighbor, lies over 4 light years away. The center of the Milky Way is about 26,000 light years from Earth. The diameter of our galaxy stretches roughly 100,000 light years. Beyond that lies intergalactic space and, eventually, the Andromeda Galaxy, resting 2.5 million light years from our home. Understanding these distances required centuries of careful observation and ingenious methods. Unlike mountains or oceans, cosmic distances cannot be measured with rulers. Astronomers must rely on light itself to estimate how far objects are from Earth. Nearby stars reveal their distances through a phenomenon known as parallax. As Earth travels around the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring these tiny changes, astronomers can calculate distance with remarkable precision. For more distant stars and galaxies, other methods become necessary. Certain stars brighten and dim in predictable ways because their true brightness is known. Astronomers can compare that brightness with how bright they appear from Earth, similar to observing a candle from different distances. The apparent brightness provides clues about how far away the object must be. Supernova explosions also serve as cosmic markers. These immense stellar events can briefly outshine entire galaxies. Since certain types of supernovae produce nearly identical amounts of light, they act as standard measuring tools across millions of light years. Through these methods, and many others, astronomers gradually constructed what is sometimes called the cosmic distance ladder, a chain of techniques that allows humanity to measure the universe step by step. The Andromeda Galaxy played a crucial role in this story. In the early 20th century, astronomers debated whether Andromeda was merely a cloud inside the Milky Way or an entirely separate galaxy. The answer came when observations revealed variable stars whose properties made them reliable indicators of distance. Calculations showed that Andromeda lay far beyond the boundaries of our galaxy. Overnight, humanity's understanding of the cosmos expanded dramatically. The discovery changed everything. If Andromeda was another galaxy, then perhaps countless other galaxies filled the universe as well. Subsequent observations confirmed exactly that. What had once seemed like the entire universe, the Milky Way, turned out to be only one galaxy among trillions. Today, telescopes can observe objects billions of light years away. Some of the most distant galaxies visible to modern instruments emitted their light when the universe itself was still very young. Looking outward into space has become equivalent to looking backward through time. Every beam of light arriving at Earth carries information from the past, preserving ancient moments across unimaginable distances. Although 2.5 million light years still sounds almost impossible to comprehend, understanding how such measurements are made provides a deeper appreciation for the extraordinary precision of modern astronomy. Through mathematics, patience, and centuries of observation, humanity has learned to measure distances so immense that even light, the fastest traveler in existence, requires millions of years to bridge the gap between neighboring galaxies. Among all the measurements used in astronomy, few are as fascinating and mysterious as the light year. The term itself often creates confusion because it sounds like a measure of time. In reality, a light year is a measure of distance, and understanding what it represents opens the door to appreciating just how immense the universe truly is. Light is the fastest thing known in nature. In the vacuum of space, it travels at nearly 300,000 kilometers every second. At that speed, light could circle Earth more than 7 times in a single second. If someone could somehow ride alongside a beam of light, they would reach the moon in just over 1 second. Sunlight takes roughly 8 minutes to reach Earth, which means that every sunrise is actually revealing the sun as it appeared 8 minutes earlier. Although these speeds are extraordinary, the universe itself is so vast that even light must spend years, centuries, and sometimes billions of years crossing the distances between celestial objects. This is why astronomers adopted the light year as a convenient way of expressing enormous separations. 1 light year represents the distance that light travels in 1 year, approximately 9.5 trillion kilometers. 9.5 trillion kilometers is a number so large that it becomes difficult to visualize. Human experience simply offers no direct comparison. Most people have traveled a few hundred kilometers in a day, perhaps a few thousand kilometers on a long flight. Circumnavigating the entire Earth covers about 40,000 kilometers. Compared with a light year, even the circumference of our planet is almost insignificant. Imagine traveling continuously at the speed of a modern jet airliner, without stopping for fuel, maintenance, or rest. Reaching the distance of 1 light year would still require well over 1 million years. During that time, entire species could evolve and disappear. Continents could change shape. Mountains could rise and erode. Such immense periods remind us that cosmic distances are intimately connected with equally astonishing stretches of time. The nearest star system to our own, Proxima Centauri, lies slightly more than 4 light years away. This means that the light arriving from that star tonight began its journey more than 4 years ago. In everyday terms, we are never seeing distant objects exactly as they are now. We are always observing them as they existed in the past. This effect becomes increasingly dramatic with larger distances. The bright star Sirius appears as it was about 8 years ago. Betelgeuse reveals itself as it existed hundreds of years in the past. The center of the Milky Way appears as it was 26,000 years ago, when human civilization had not yet emerged. Looking farther still, the Andromeda Galaxy appears as it existed approximately 2.5 million years ago. At that time, early human ancestors were only beginning to walk across Africa. Ice ages had not yet shaped much of the world we recognize today. Entire species that once inhabited Earth had yet to appear. The light reaching our eyes from Andromeda has been traveling through space during all of this history, moving silently and uninterrupted across the vast darkness separating galaxies. In a sense, every telescope is a time machine. Astronomers cannot travel into the past, but by observing distant objects, they can witness ancient events. Light acts as a messenger carrying information across the cosmos. Some galaxies visible to modern observatories are so distant that their light began its journey billions of years ago, long before Earth itself existed. This remarkable fact changes the way we think about the universe. Space and time become deeply connected. Looking farther into space means looking farther into history. The night sky is not a snapshot of a single moment. Instead, it is a collection of countless moments from different eras, all arriving simultaneously at Earth. Understanding the light year also reveals how isolated stars truly are. In science fiction, spacecraft often leap effortlessly between star systems. Reality is much quieter and far more challenging. Even neighboring stars are separated by distances so enormous that conventional travel methods become almost meaningless. If humanity hopes to explore beyond the solar system, entirely new technologies and ways of thinking may be required. The scale becomes even more astonishing when considering galaxies. The Milky Way spans roughly 100,000 light years from one side to the other. A beam of light, traveling at the maximum speed allowed by nature, would require 100,000 years to cross our galaxy completely. Human history occupies only a tiny fraction of that time span. Andromeda lies 25 times farther away than the width of the Milky Way. 2.5 million light years sounds like a single number, but hidden within that figure is a journey that stretches beyond ordinary imagination. Even light, the ultimate speed limit of the universe, needs millions of years to complete the voyage. Despite these enormous scales, the universe remains interconnected through the steady movement of light. Every star visible in the sky is sending streams of information outward in all directions. Some of those photons eventually arrive at Earth, allowing humanity to piece together the story of the cosmos. Through light, we learn about stars that have long since disappeared, galaxies that existed before our planet formed, and events that unfolded across unimaginable distances. Perhaps one of the most beautiful aspects of the light year is that it reminds us how precious and unusual our own lives are. Human beings live for decades. Civilizations endure for thousands of years. Yet the universe measures itself in millions and billions of years. Against such a backdrop, the faint glow of Andromeda becomes something even more extraordinary. Those ancient photons, having traveled for 2.5 million years through nearly empty space, eventually encounter a small blue planet orbiting an ordinary star, where curious minds gaze upward and wonder how long it would take to make the same journey themselves. When people imagine the universe, they often picture a crowded place filled with stars, planets, colorful nebulae, and countless celestial objects packed closely together. Movies and illustrations frequently show spacecraft weaving between stars as though they were buildings in a city. In reality, the universe is far quieter and far emptier than these images suggest. One of the greatest surprises awaiting anyone who begins studying astronomy is discovering just how much of the cosmos consists of almost nothing at all. Our own solar system offers the first clue. Although diagrams in textbooks often show the planets lined up neatly beside one another, these illustrations are greatly compressed. If the sun were the size of a large ball placed at one end of a field, Earth would be a tiny object located many meters away. Jupiter would lie much farther still, and Neptune would be so distant that most of the field would contain only empty space. Even within the solar system, emptiness dominates. The planets themselves occupy only a tiny fraction of the available volume. Between Earth and Mars stretches a vast region containing almost nothing. Spacecraft traveling between planets spend months crossing this silent emptiness. Most of their journey involves passing through darkness with no nearby landmarks and no dramatic obstacles. Beyond the planets lies an even greater emptiness. The nearest star system, Proxima Centauri, is more than 4 light-years away. This distance is so large that if the sun were reduced to the size of a marble, the nearest star would be another marble located hundreds of kilometers away. Between them would exist almost entirely empty space. The stars inside the Milky Way are not packed together like grains of sand. On average, each star is separated from its nearest neighbors by several light years. If our sun and the surrounding stars were represented by houses, entire countries could fit between them. Looking up into the night sky, thousands of stars appear close together, but this is an illusion created by perspective. In reality, they are separated by enormous distances. The emptiness becomes even more striking when considering galaxies. The Milky Way contains hundreds of billions of stars spread across roughly 100,000 light years. Although this number sounds immense, the volume occupied by the galaxy is even more enormous. Most of that region contains very little matter. There are clouds of gas, regions of dust, and occasional clusters of stars, but vast expanses remain nearly empty. Then comes intergalactic space, the region separating the Milky Way from the Andromeda Galaxy. This is where the concept of emptiness reaches almost unimaginable levels. Between the two galaxies lies a gulf of approximately 2.5 million light years. Contrary to what many people expect, this region is not filled with stars. Instead, it contains only extremely thin gas and invisible dark matter spread across distances so vast that individual atoms may be separated by many centimeters or even meters. On Earth, even the most powerful vacuum chambers still contain billions upon billions of particles. Intergalactic space is far emptier than anything humans can create in laboratories. If someone could somehow float in this region, they would find themselves surrounded by darkness so profound that nearby stars would appear as distant points of light, scattered across an endless void. This emptiness creates both challenges and advantages for future explorers. On one hand, the lack of obstacles means that a spacecraft traveling toward Andromeda would not need to dodge countless stars or planets. Collisions with large objects would be extremely unlikely. In fact, the probability of accidentally striking another star during the journey would be almost zero. On the other hand, emptiness presents its own difficulties. There are no gas stations in intergalactic space. No planets provide resources. No nearby stars offer warmth or energy. A spacecraft making such a voyage would have to carry everything necessary for survival or possess technologies capable of generating resources independently for periods far exceeding human history. Even galaxies themselves can pass through one another with surprisingly few collisions. Astronomers predict that the Milky Way and Andromeda will eventually merge billions of years from now, despite the enormous number of stars involved. Direct collisions between individual stars are expected to be exceedingly rare. This is because stars are tiny compared with the immense distances separating them. The emptiness of the universe can sometimes feel lonely, but it also reveals something profound. Matter is precious. The atoms making up planets, oceans, mountains, and living beings are rare concentrations within an ocean of nearly empty space. Everything familiar to human experience exists in small islands scattered across a cosmos dominated by vast stretches of darkness. Strangely enough, even the atoms inside our own bodies are mostly empty space. Atoms consist of tiny nuclei surrounded by clouds of electrons, and the distances involved are enormous compared with the sizes of the particles themselves. If an atom were enlarged to the size of a cathedral, its nucleus would be no larger than a grain of sand. The rest would consist almost entirely of emptiness. In this sense, emptiness exists on every scale. It separates particles within atoms, planets within solar systems, stars within galaxies, and galaxies themselves. Yet from these rare pockets of matter emerge oceans, forests, civilizations, and conscious beings capable of asking questions about the universe. For anyone imagining a voyage to Andromeda, understanding this emptiness is essential. The greatest obstacle would not be navigating through crowded regions of stars or avoiding dangerous celestial traffic. The true challenge would be enduring the unimaginable distances and times involved while crossing an ocean of darkness, so vast and so empty that even light itself requires millions of years to complete the journey. Against this backdrop of cosmic silence, the glowing spiral of Andromeda becomes even more remarkable. It shines like a distant island of stars suspended across an immense sea of nothingness, waiting patiently on the far side of one of the largest empty regions that humanity can easily observe in the night sky. To understand how long it would take to reach the Andromeda Galaxy, it helps to begin with something far more familiar: human speed. Before thinking about spacecraft crossing millions of light years, it is useful to look at the fastest journeys ever achieved by human technology, and how those speeds compare with the scale of interstellar and intergalactic space. On Earth, human travel is limited by the environment. Cars, trains, and airplanes all operate within the boundaries of atmosphere, gravity, and engineering constraints. Commercial airplanes typically travel at speeds around 800 to 900 kilometers per hour. At that speed, crossing a large country can take hours, and crossing an ocean can take more than 10 hours. Even though airplanes feel fast in everyday life, they are extremely slow compared with anything in space. Spacecraft, once they leave Earth's atmosphere, can reach much higher speeds. The reason is simple. There is no air resistance in space, and once a vehicle is accelerated, it can continue moving with very little need for additional energy. However, escaping Earth's gravity well requires a tremendous amount of energy, which limits how fast human missions can initially travel. One of the fastest human-made objects ever launched is the Parker Solar Probe. This spacecraft was designed to study the sun by traveling extremely close to it. As it falls deeper into the sun's gravitational field, it gains speed. At its closest approach, it has reached speeds exceeding hundreds of thousands of kilometers per hour. This is far faster than any airplane or jet, and far faster than most previous spacecraft. Even with these extraordinary speeds, the scale of space remains overwhelming. If the Parker Solar Probe were directed toward the nearest star system, Proxima Centauri, it would still take thousands of years to arrive. This is because even 4 light years is an enormous distance when compared with any achievable human technology. The Apollo missions, which took humans to the moon, provide another useful reference point. The spacecraft traveled at speeds of roughly 40,000 kilometers per hour during parts of their journey. At that speed, reaching the moon took about 3 days. This feels long by modern travel standards, but it is extremely fast compared with any other form of human exploration beyond Earth. Voyager 1, launched in 1977, is another important milestone. It is currently the farthest human-made object from Earth. After decades of travel, it has entered interstellar space, meaning it has passed beyond the influence of the sun's solar wind. However, despite traveling for nearly half a century, Voyager 1 has moved only a tiny fraction of the distance to even the nearest star. If we scale its journey to the distance of a city, it has barely left the neighborhood. This comparison reveals something essential. The speed of human spacecraft, even the fastest ones, is still extremely small compared with the distances between stars. Space is not only large, it is overwhelmingly large relative to our current technological capabilities. To better understand this limitation, imagine scaling down the Milky Way galaxy to a size that fits on Earth. Even in such a reduced model, the nearest stars would still be separated by vast distances. Now extend that comparison to Andromeda, which is even farther away. The gap becomes so large that even the fastest spacecraft would require millions or billions of years to cross it. There is also an important difference between speed and energy. Increasing speed in space is not simply a matter of pressing harder on an engine. Every increase in velocity requires exponentially more energy. This is one of the fundamental challenges of physics and engineering. As a spacecraft approaches higher fractions of the speed of light, the energy required becomes so large that it exceeds anything humanity can currently produce. Another limitation is fuel. Rockets must carry their own fuel, which adds weight. More weight requires more fuel, which adds even more weight. This creates a cycle that makes extremely fast travel increasingly difficult. Even advanced concepts like ion propulsion or nuclear engines only partially reduce this problem. Because of these limitations, human space exploration has so far remained within a relatively small region of the solar system. We have sent probes to the outer planets, landed robots on Mars, and studied distant asteroids, but the vast majority of interstellar space remains untouched by human technology. When we compare human speeds to the distance of Andromeda, the gap becomes almost unimaginable, even traveling at the speed of the fastest spacecraft ever built. Reaching Andromeda would take far longer than the current age of the universe. This is because 2.5 million light-years is not just a large distance. It is a scale that belongs to galaxies, not planets or stars. Still, these achievements are not meaningless. Each spacecraft launched by humanity represents a step forward in understanding how to move through space. Voyager 1, Parker Solar Probe, and future missions all contribute pieces of knowledge that may one day lead to faster and more efficient travel methods. For now, however, the universe sets a clear boundary. Human travel is fast on Earth, moderately fast in space, but still incredibly slow compared with the distances between stars and galaxies. Andromeda remains far beyond any current capability, a destination defined more by imagination and mathematics than by engineering. As the quiet journey through these concepts continues, it becomes increasingly clear that the question is not only how long it would take to reach Andromeda, but what kind of civilization would ever be capable of moving fast enough, or enduring long enough, to make such a journey possible. Among all human-made objects drifting through space, Voyager 1 holds a special place. It is not the fastest spacecraft ever built, nor the most powerful, but it represents something far more meaningful. The first time humanity managed to send a functioning object beyond the boundaries of the solar system and into interstellar space. When thinking about how long it would take to reach Andromeda, Voyager 1 becomes a quiet reference point, a reminder of how small even our greatest achievements are when measured against galactic distances. Voyager 1 was launched in 1977, during a period when computers were still large, communication systems were limited, and space exploration was still in its early stages. Its mission was originally focused on the outer planets, especially Jupiter and Saturn. It was never designed with interstellar travel in mind. Yet after completing its planetary encounters, it continued moving outward, carried by its own momentum, slowly leaving the influence of the Sun behind. Over the decades, Voyager 1 crossed several invisible boundaries. First, it passed the orbit of Pluto, then the termination shock where the solar wind slows down, and eventually it entered interstellar space. This region is not empty, but it is vastly different from the solar system. Here, the Sun's influence weakens, and particles from other stars begin to dominate the environment. It is a subtle transition, but an important one, marking the spacecraft's departure from its home system. Despite this achievement, Voyager 1 is still incredibly close to the starting line of a galactic journey. After nearly 50 years of travel, it has moved only a tiny fraction of the distance to the nearest star. If we imagine the distance between the Sun and Andromeda compressed into a straight line, Voyager 1 would be almost indistinguishable from the starting point. It is a reminder that even the most persistent human technology is still bound to the early stages of cosmic exploration. Voyager 1 travels at roughly 17 kilometers per second relative to the Sun. This is extremely fast by Earth standards. In 1 second, it covers a distance longer than many city highways combined. In 1 hour, it travels more than 60,000 kilometers. Yet even at this speed, the journey to Andromeda would take an incomprehensible amount of time, far exceeding anything related to human civilization or even planetary history. To understand this better, imagine Voyager 1 traveling not just through the solar system, but directly toward Andromeda. At its current speed, it would require billions upon billions of years to reach that distant galaxy. This time span is so large that it exceeds the current age of the universe itself. In other words, even if Voyager 1 had been launched at the moment of the Big Bang, it would still not have reached its destination. What makes this even more striking is that Voyager 1 is not slow compared to other spacecraft. In fact, it is one of the fastest objects ever created by humanity that continues to move outward on its own. There are faster probes in certain moments of their trajectory, such as those falling toward the Sun, but Voyager 1 represents sustained velocity over an extremely long duration. The spacecraft also carries a symbolic message. Attached to its structure is the Golden Record, a small phonograph disc containing sounds, images, and greetings from Earth. It includes music from different cultures, natural sounds like wind and ocean waves, and mathematical instructions for decoding the information. It is a message intended for any potential intelligence that might encounter it in the distant future. While the likelihood of Voyager 1 ever being found by another civilization is extremely small, the gesture itself carries meaning. It represents humanity's desire to reach beyond its own world, to communicate across vast distances, and to leave a trace of its existence in the cosmos. In the context of Andromeda, this gesture becomes almost poetic. A tiny spacecraft drifting through the local region of the Milky Way, while an entire galaxy lies millions of light years away, untouched and unreachable by anything we have built. Voyager 1 also helps illustrate the concept of scale in a very tangible way. If its entire journey were compressed into a human lifetime, the distance to Andromeda would stretch far beyond imagination. The spacecraft's path would become a small line near the beginning of an almost infinite expanse. This comparison helps ground abstract numbers into something more understandable, even if the true scale still escapes intuition. Another important aspect of Voyager 1 is its endurance. The spacecraft continues to send weak signals back to Earth, even after decades in space. These signals take hours to reach us due to distance, and they grow weaker every year as the spacecraft drifts farther away. Eventually, its power source will fade, and communication will cease. At that point, Voyager 1 will continue silently into interstellar space, carrying its golden record and its legacy without any connection to Earth. This slow fading highlights a key reality of space exploration. Distance is not just about how far something is, but also about how communication weakens over time. Even sending a message to another star system would require years for a response. At the scale of Andromeda, communication becomes effectively impossible within human timescales. Yet Voyager 1 remains important because it marks the beginning of a new era. It is the first step, however small, toward understanding what it means to travel beyond our solar system. It shows that humanity is capable of reaching interstellar space, even if only with small robotic probes. And from this beginning, future technologies may one day expand our reach further, perhaps even toward distant stars and in unimaginable futures toward other galaxies. For now, however, Voyager 1 drifts in quiet darkness, surrounded by the vast emptiness between stars, while Andromeda remains an unreachable beacon in the distance, waiting far beyond the limits of our current journey. If all of humanity's current technology were directed toward a single goal, reaching the Andromeda Galaxy, the result would still be a journey so long that it escapes ordinary comprehension. Even after understanding distances, speeds, and spacecraft like Voyager 1, the final calculation reveals something even more overwhelming. Present technology is not just slow, it is almost completely insufficient for intergalactic travel. The distance to Andromeda is approximately 2.5 million light years. A light year is the distance light travels in 1 year, and light itself is the fastest known phenomenon in the universe. So the simplest way to think about the journey is to imagine how long light would take. Light already takes 2.5 million years to cross that distance. This sets a baseline that no physical object can beat under known laws of physics. Human technology, even at its best, moves at only a tiny fraction of light speed. Voyager 1, one of the fastest spacecraft ever built, travels at about 17 kilometers per second. Light travels at about 300,000 kilometers per second. This means Voyager 1 moves at roughly 1/20,000th the speed of light. That difference alone completely reshapes the idea of intergalactic travel. If Voyager 1 were aimed directly at Andromeda, the journey would take on the order of tens of billions of years. This number is difficult to place in context because it exceeds the current age of the universe, which is about 13.8 billion years. In other words, using current technology, reaching Andromeda is not just impractical, it is longer than the entire history of everything we know. Even if we imagine significant improvements, such as chemical rockets being replaced with advanced ion engines or nuclear propulsion systems, the situation changes only slightly on a cosmic scale. Ion engines can operate efficiently for long periods, but they still produce very small thrust compared with the energy required for interstellar speeds. Nuclear propulsion concepts offer more power, but still fall far short of what would be needed to make galaxy crossing a realistic endeavor. To understand this limitation more clearly, it helps to think in terms of exponential scaling. Increasing speed in space is not linear. Doubling the speed of a spacecraft does not have the difficulty of the journey in a meaningful way when distances become so extreme. The difference between a journey lasting millions of years and one lasting tens of millions of years, may seem small in mathematical terms, but for civilizations, both are effectively unreachable. Even if humanity were able to construct a spacecraft traveling at 1% of the speed of light, which is far beyond current capability, the journey to Andromeda would still take about 250 million years. This is longer than the existence of many species on Earth, and far longer than the entire history of mammals. Civilization itself would have to evolve through countless stages just to remain in existence long enough to witness arrival at 10% of the speed of light, which would require technologies far beyond anything currently known. The journey would still take around 25 million years. At that point, even geological processes on Earth would reshape continents, and entire cycles of ice ages would come and go repeatedly. These comparisons reveal a deeper truth about intergalactic travel. The problem is not simply engineering. It is time itself. The universe operates on timescales that dwarf biological, geological, and even stellar processes. A journey to Andromeda is not a voyage that can be planned within a human civilization. It is a project that would require civilizations to persist far longer than anything in recorded or even geological history. Another key limitation is energy. Accelerating a spacecraft to relativistic speeds requires enormous amounts of energy. As speed increases, relativistic effects also begin to appear. The closer an object moves to the speed of light, the more energy is required to increase its speed further. This creates a natural barrier that makes reaching light speed impossible for objects with mass under known physics. Because of these limitations, most realistic discussions of interstellar travel focus on much smaller distances, such as nearby star systems within 10 or 20 light years. Even these journeys would take decades or centuries using advanced propulsion systems. Andromeda, at millions of light years away, exists in a completely different category, one that belongs more to theoretical physics and cosmic imagination than to engineering. There is also the issue of navigation over such immense distances. Space is not static. Galaxies move, stars orbit, and gravitational interactions constantly reshape cosmic structure. Over millions of years, the position of Andromeda relative to the Milky Way will change significantly. In fact, the two galaxies are slowly moving toward each other, meaning the concept of traveling to a fixed point in space becomes even more complex. Even if a spacecraft could leave the Milky Way, it would not be aiming at a stationary target. It would need to account for cosmic motion on a scale that unfolds over millions of years. This adds another layer of difficulty that current technology cannot even begin to address. Despite all of these limitations, the thought experiment itself remains valuable. It highlights the boundaries of human capability and helps define the scale of the universe in a more tangible way. Understanding that present technology would require tens of billions of years to reach Andromeda does not diminish scientific progress. Instead, it emphasizes how extraordinary even our small steps into space truly are. Every satellite, probe, and telescope represents a step outward from Earth into regions once thought unreachable. While Andromeda remains far beyond our grasp, the act of studying it, measuring it, and imagining a journey toward it reflects a fundamental human trait: the desire to explore even when the destination lies far beyond practical reach. In the quiet vastness of space, present technology reaches its limit long before the destination appears. And yet, even within those limits, humanity continues to expand its understanding, slowly mapping the invisible path between where we are and where we may never physically go. Before moving deeper into speculative propulsion systems and future interstellar ideas, it is useful to return once again to something grounded in everyday reality: commercial aircraft. These machines represent one of the most common forms of high-speed travel for humans, and yet, when placed against the scale of intergalactic distances, they become almost motionless. A typical passenger airplane cruises at around 800 to 900 kilometers per hour. At first glance, This feels fast. Cities disappear beneath clouds. Countries pass by in hours, and continents can be crossed within a single day. For human experience, this speed is impressive and efficient. It defines modern global connectivity, allowing people to move between distant parts of the world in relatively short times. However, when this speed is extended into space, the illusion of rapid movement dissolves completely. The Earth itself is only about 40,000 kilometers in circumference. At airplane speed, circling the entire planet would take roughly 40 to 50 hours without stops. That already stretches human patience, but it is still within a manageable time frame. Once we move beyond Earth, the scale changes entirely. The Moon is about 400,000 kilometers away. At commercial aircraft speed, reaching it would take roughly 20 days of continuous flight. That is already far beyond practical aviation limits, but still within the realm of imagination. Now extend that same logic further outward. The Sun is 150 million kilometers away. At airplane speed, reaching the Sun would take more than 17,000 years. This comparison reveals an important truth. Aircraft speed belongs entirely to the scale of planetary travel. It is perfectly suited for crossing oceans and continents, but it is completely incompatible with space distances. The moment we leave Earth's immediate environment, the usefulness of such speeds collapses rapidly. Now consider the Milky Way galaxy. Its diameter is approximately 100,000 light years. Converting that into kilometers produces a number so large that it becomes almost meaningless in human terms. At airplane speed, crossing even a single light year would take more than 1,000,000 years. Crossing the entire galaxy would take far longer than the existence of complex life on Earth. When we extend this comparison to Andromeda, the result becomes even more extreme. At commercial aircraft speed, the journey of 2.5 million light years transforms into a duration that exceeds tens of billions of years. This is far beyond the age of the Earth, the Sun, and even the universe itself. In practical terms, it is not a journey, but an impossibility. The key reason for this limitation is not only speed, but also the nature of space itself. Space is not designed for human-scale movement. On Earth, distances are compressed into environments where speed can meaningfully reduce travel time. Roads, skies, and oceans all exist within a relatively small sphere. In space, however, even the nearest objects are separated by incomprehensible gaps. Another factor is energy efficiency. Aircraft rely on air for lift and propulsion. Without an atmosphere, they cannot function at all. This makes them fundamentally Earth-bound machines. Even if one could somehow imagine an aircraft continuing into space, it would quickly lose all ability to operate. The engines, wings, and aerodynamic systems are all designed for conditions that do not exist beyond Earth. This highlights a broader idea in space exploration. Every technology is limited by the environment it was designed for. Aircraft belong to the atmosphere. Rockets belong to escape trajectories from planetary gravity. Spacecraft belong to vacuum conditions. But even spacecraft, as advanced as they are still bound by the limits of energy, fuel, and physics. When imagining travel to Andromeda, aircraft speed serves as a useful reference point, not because it is practical, but because it illustrates the extreme gap between human experience and cosmic reality. It shows how the fastest familiar things on Earth are almost frozen in place when measured against intergalactic distances. If a commercial airplane could somehow maintain its speed in space, it would still not reach the nearest star within millions of years. It would not come close to crossing the Milky Way, and Andromeda would remain entirely unreachable, a destination so distant that the aircraft would effectively never arrive, no matter how long it continued to fly. Yet this comparison is not meant to discourage curiosity. Instead, it reveals how extraordinary even small advances in speed truly are. The difference between walking, driving, Flying and launching spacecraft represents enormous progress in human capability. Each step has expanded the boundaries of exploration within its own domain. In the quiet context of cosmic scales, aircraft become a reminder of where humanity currently stands. We have mastered the skies of our planet, but we have only begun to touch the edges of space. The journey to Andromeda remains far beyond any aircraft, any rocket, or any current technology. It exists in a realm where even imagination must stretch to keep up with the numbers involved. As the thought of crossing such distances settles in, the contrast becomes almost peaceful. The steady hum of an airplane engine, once a symbol of speed and modern life, fades into something much smaller when placed against the silent expanse between galaxies. And somewhere far beyond that silence, Andromeda continues to drift, wading across millions of light years of empty space. Human aircraft belong to the atmosphere, but spacecraft represent humanity's first real attempt to leave it behind. Once a vehicle escapes Earth's air and reaches space, a different set of physical rules begins to dominate its motion. Without air resistance, objects can maintain extremely high speeds for long periods, and some missions are designed specifically to push these limits. Among all human-made machines, a few spacecraft stand out as the fastest ever created, and they help define the upper boundary of what current technology can achieve. One of the most remarkable examples is the Parker Solar Probe. This spacecraft was designed with a very specific purpose: to study the sun by traveling closer to it than any previous mission. As it approaches the sun, it falls deeper into the sun's gravitational field, and this gravitational pull accelerates it to extraordinary speeds. At its closest approach, it reaches velocities exceeding hundreds of kilometers per second, making it the fastest human-made object ever built. This speed is difficult to comprehend in everyday terms. In 1 second, the probe can travel a distance comparable to crossing entire countries. In 1 minute, it can cover distances that would take commercial aircraft many hours. Yet even at this incredible velocity, the universe remains overwhelmingly large compared to its motion. If the Parker Solar Probe were redirected toward the nearest star system, Proxima Centauri, it would still require thousands of years to complete the journey. This is because 4 light years, while small in cosmic terms, still represents an enormous gulf in space. Even a spacecraft traveling at extreme speeds within the solar system is still moving at a tiny fraction of the speed of light. Now, consider Andromeda. At 2.5 million light years away, the gap becomes almost incomprehensible. Even if we take the fastest speed achieved by the Parker Solar Probe and imagine it sustained continuously in a straight line toward Andromeda, the journey would extend into timescales that exceed tens of billions of years. This far surpasses the age of Earth and even the age of the observable universe. What makes this comparison important is not just the number itself, but what it reveals about scale. The difference between interplanetary travel and intergalactic travel is not incremental. It is exponential. A spacecraft that feels extremely fast within the solar system becomes almost stationary when viewed from the perspective of galaxy to galaxy distances. Another important spacecraft in this context is the Voyager series, especially Voyager 1. Although it is slower than the Parker Solar Probe at peak speed, Voyager 1 represents long-term sustained travel away from the sun. It has been moving outward for decades, gradually escaping the influence of the solar system. Its journey shows that persistence in space is possible, even if the speed is modest. However, even Voyager 1 is still extremely close to the starting line when measured against interstellar distances. It has traveled only a tiny fraction of the distance to the nearest stars, and an almost negligible fraction of the distance to Andromeda. If the entire journey to Andromeda were scaled down to the length of a city, Voyager 1 would barely have left a single street. This highlights a key limitation of current spacecraft technology. They are not constrained by direction or stability, but by speed itself. No matter how efficiently a spacecraft is designed, it still must obey the limits of energy, propulsion, and relativistic physics. Increasing speed beyond a certain point requires exponentially more energy, making significant improvements increasingly difficult. Even if future spacecraft could maintain speeds far beyond anything currently achievable, the challenge of reaching Andromeda would remain immense. The intergalactic distance is so large that even small fractions of light speed result in journeys lasting millions or billions of years. This transforms the concept of travel from an engineering problem into a question of civilization scale and endurance. There is also a subtle but important difference between speed achieved near the sun and speed in deep space. Many spacecraft reach their highest velocities only during brief moments, often when influenced by strong gravitational fields. Once they leave these regions, their speed stabilizes or decreases. Sustaining extreme velocity over millions of years would require propulsion systems far beyond anything currently known. As we reflect on the fastest spacecraft humanity has ever created, a pattern becomes clear. Each improvement in speed opens new regions of the solar system for exploration, but the leap required to reach even nearby stars remains enormous. The leap required to reach Andromeda is far beyond that, placing it in a category where current physics sets strict and unavoidable limits. Still, these spacecraft represent an important beginning. They are proof that humanity can build machines capable of leaving Earth, surviving in space, and traveling for decades without intervention. They are the first steps on a path that, while currently short, may eventually expand into much larger scales of exploration. For now, however, even the fastest spacecraft ever built move like slow drifting sparks when compared with the vast ocean of space between galaxies. Andromeda remains distant, not because humanity lacks curiosity, but because the universe itself sets a scale that stretches far beyond the reach of present technology. Among all the limits in physics, the speed of light stands as one of the most important. It is not just a fast speed, but a boundary that defines how space, time, and energy behave in the universe. Light travels at about 300,000 kilometers every second, and nothing with mass is known to reach or exceed this speed. Yet imagining what would happen if we could travel at or near this limit helps reveal what a journey to Andromeda would truly look like under the most extreme possible conditions. If a spacecraft could travel at the speed of light, the distance between the Milky Way and Andromeda would become simple to describe. 2.5 million light years would mean a journey of 2.5 million years. This is because a light year is defined by how far light travels in 1 year. At light speed, distance and time become directly linked in a simple one-to-one relationship. Even in this idealized scenario, the journey is still enormous. 2.5 million years is a time span far longer than the existence of human civilization, and far longer than the appearance of modern humans on Earth. Entire ice ages would begin and end many times during such a voyage. Continents would shift, oceans would reshape, and species would evolve into entirely new forms while the spacecraft continues its silent journey through intergalactic space. However, reaching the speed of light is not physically possible for any object with mass, according to our current understanding of physics. As an object approaches light speed, its energy requirements increase dramatically. The closer it gets to the speed of light, the more energy is needed to continue accelerating. At the exact speed of light, the required energy becomes infinite, which means it cannot be reached in reality. This limitation introduces a deeper layer of understanding. Even imagining light speed travel does not fully solve the problem of reaching Andromeda. It only provides a theoretical baseline. In practice, any spacecraft would travel slower, which immediately extends the journey beyond 2.5 million years into even longer timescales. If we consider a spacecraft traveling at 99% of the speed of light, the journey becomes slightly shorter due to relativistic effects. but still remains on the scale of millions of years from an outside observer's perspective. This is where the strange nature of relativity begins to appear. According to relativity, time is not absolute. It changes depending on speed. For an object moving close to the speed of light, time slows down relative to an outside observer. This means that while millions of years may pass in the rest of the universe, the travelers inside the spacecraft would experience a much shorter subjective duration. At extremely high speeds, time dilation becomes significant. A journey that appears to take millions of years from Earth might feel like only decades or centuries to those on board. This creates a strange dual reality. Outside observers see a slow cosmic voyage, while travelers experience a compressed version of time. Even with this effect, the universe does not become smaller. The distance to Andromeda remains the same in space, but time behaves differently depending on perspective. This is one of the most counterintuitive aspects of modern physics. Space and time are not separate entities, but parts of a single structure that bends and stretches depending on motion and gravity. If future technology ever allowed spacecraft to reach extremely high fractions of light speed, human perception of long journeys might change dramatically. A crew traveling toward Andromeda might age slowly relative to the rest of the universe, while billions of years pass outside their frame of reference. However, achieving and sustaining such speeds would require energy sources and materials far beyond anything currently imaginable. There is also another limitation. Even if a spacecraft could somehow approach light speed, intergalactic space is not entirely empty. While it is extremely sparse, it still contains particles, radiation, and cosmic dust. At near light speed, even a single particle collision could release enormous amounts of energy, creating dangerous conditions for any physical object traveling through it. This introduces another layer of difficulty. High-speed travel is not just about propulsion. It is also about survival in an environment where even the smallest particle becomes a potential hazard. Shielding a spacecraft against such conditions would require technologies that are currently beyond engineering capability. Despite these challenges, the idea of light-speed travel remains useful for understanding cosmic distances. It provides a universal ruler for the universe. When we say Andromeda is 2.5 million light-years away, we are effectively saying that even light itself requires 2.5 million years to bridge the gap. This fact alone places the galaxy into a scale that transcends human history. It means that every image we see of Andromeda is not a snapshot of the present, but a reflection of deep time. We are always looking into the past when we observe distant galaxies. In the end, even the concept of light-speed travel does not bring Andromeda within practical reach. It only reveals the true nature of the distance separating us from it. The galaxy remains both physically real and effectively unreachable within any reasonable time frame. As the thought settles, it becomes clear that Andromeda is not just far away. It exists in a different temporal scale of the universe, where journeys are measured not in human lifetimes, but in epochs that stretch across civilizations, stars, and entire galactic histories. When imagining a journey to the Andromeda Galaxy at speeds close to the speed of light, the simple idea of distance and time begins to break apart. In everyday life, time feels steady and universal. 1 second is always 1 second, no matter where you are or how fast you move. Space also feels fixed, with distances remaining the same regardless of motion. But in the universe at extreme speeds, these assumptions no longer hold. This is where relativity becomes important. It shows that time and space are not separate, rigid structures. Instead, they are connected and flexible, changing depending on motion and gravity. At speeds close to the speed of light, time itself begins to slow down for the traveler compared to someone who remains at rest. If a spacecraft were traveling toward Andromeda at a significant fraction of the speed of light, something unusual would happen. From the perspective of an observer on Earth, the journey would still appear to take millions of years. The distance between galaxies would remain unchanged. and the spacecraft would slowly cross the vast emptiness of intergalactic space. However, for the people inside the spacecraft, the experience would be very different. Time would pass more slowly for them compared to the outside universe. This means that while millions of years might pass outside, the crew might experience far less time during the same journey. The closer the spacecraft gets to the speed of light, the stronger this effect becomes. This difference in time perception is called time dilation. It is not a trick of perception or measurement error. It is a real physical effect confirmed by experiments with fast-moving particles and precise atomic clocks. Even on Earth, tiny versions of this effect can be measured when objects move at high speeds or when clocks are placed at different gravitational strengths. At near light speeds, time dilation becomes extreme. A journey that takes millions of years according to distant observers might feel like only decades or centuries for the travelers themselves. This creates a strange situation where the universe outside continues evolving, while the travelers experience a much slower passage of time. Another effect of relativity is length contraction. From the perspective of the moving spacecraft, distances in the direction of motion become shorter. This means that the space between the Milky Way and Andromeda would appear compressed. Instead of millions of light years, the travelers might perceive a much shorter distance, depending on how close they are to the speed of light. Together, time dilation and length contraction work in a balanced way. They ensure that the laws of physics remain consistent for all observers, even when they are moving at extreme speeds relative to one another. The universe does not favor one perspective over another. Instead, it allows different observers to experience reality in different but mathematically consistent ways. This leads to one of the most fascinating ideas in physics. A journey to Andromeda could, in theory, feel very different depending on who is observing it. From Earth, it is a voyage lasting millions of years. From inside a near-light speed spacecraft, it could feel dramatically shorter. Yet both descriptions are correct within their own reference frames. However, this does not solve the fundamental challenge of intergalactic travel. Even if time is reduced for the travelers, the energy required to reach such speeds remains enormous. Accelerating a spacecraft to near-light speed requires amounts of energy that grow rapidly as speed increases. The closer one gets to light speed, the more energy is needed for even the smallest increase in velocity. There is also the issue of deceleration. Reaching Andromeda is not just about getting there quickly. A spacecraft would also need to slow down upon arrival. Without deceleration, it would pass through the galaxy without any chance of exploration or interaction. Slowing down at such speeds would require energy comparable to or even greater than the energy used for acceleration. Inside the spacecraft, another challenge would emerge. At extreme speeds, even tiny particles in space become dangerous. A grain of dust, nearly invisible in normal conditions, would carry enormous energy when hit at near light speed. Shielding a spacecraft against such impacts would require materials and technologies far beyond anything currently available. Relativity also introduces a deeper philosophical effect. As time slows for travelers, they effectively become separated from the rest of the universe's history. While they move through space, the outside universe continues evolving at a much faster rate. Stars are born and die, galaxies change shape, and cosmic structures shift while the travelers experience only a fraction of that passage. In a sense, traveling close to the speed of light is not just moving through space. It is also moving through time at a different rate. This makes intergalactic travel not only a physical challenge, but also a temporal one. The journey to Andromeda becomes a question of how different observers experience the unfolding of the universe itself. Despite these strange effects, relativity does not reduce the distance to Andromeda in any absolute sense. The galaxy remains 2.5 million light-years away. What changes is the relationship between time, space, and motion. The universe becomes flexible rather than fixed, shaped by the speed at which an observer moves through it. As the quiet thought of this journey continues, it becomes clear that traveling to Andromeda is not just about crossing space. It is about entering a regime where reality itself behaves differently, depending on perspective. And in that shifting relationship between time and distance, the universe reveals just how strange and interconnected its fundamental structure truly is. If the journey to the Andromeda Galaxy feels impossible with today's spacecraft, the natural question becomes whether future technology could change that outcome. Human history shows a steady pattern of improvement in travel and exploration. From walking, to sailing, to flight, and eventually to rockets, each era has expanded the boundaries of movement. It is tempting to imagine that the same progression might one day extend beyond the solar system, and even beyond the Milky Way itself. To understand this possibility, it is important to first recognize what limits current propulsion systems. Most spacecraft today rely on chemical rockets or ion engines. Chemical rockets generate large bursts of thrust by burning fuel, but they are inefficient for long-distance travel. Ion engines are far more efficient and can operate continuously for long periods, but they produce very low thrust. Both systems are constrained by the need to carry reaction mass, meaning they must bring their own fuel for acceleration. This creates a fundamental limitation. The more fuel a spacecraft carries, the heavier it becomes. The heavier it becomes, the more fuel it needs to accelerate. This feedback loop makes it extremely difficult to reach very high speeds, even in the most advanced designs. A significant portion of the spacecraft's mass is devoted to fuel rather than payload or instruments. Because of this, most realistic future concepts for interstellar travel involve entirely new approaches to propulsion. One of the most widely discussed ideas is nuclear propulsion. Instead of relying on chemical reactions, nuclear engines would use energy released from atomic reactions, which is far more concentrated. In theory, this could allow spacecraft to reach much higher speeds than current rockets. However, even nuclear propulsion has limits. While it could significantly improve travel times within the solar system and perhaps enable missions to nearby stars, the energy required to reach even a fraction of light speed remains enormous. The journey to Andromeda would still be far beyond its capabilities. Another concept involves fusion propulsion. Fusion, the process that powers stars, releases even greater amounts of energy than nuclear fission. If humanity ever learns to control fusion efficiently in spacecraft, it could open the door to much faster interstellar travel. Fusion-driven rockets could potentially reach a few percent of the speed of light under ideal conditions. Even at a few percent of light speed, however, the journey to Andromeda would still take millions of years. This highlights a key truth. Improving propulsion technology reduces travel time, but only up to a point. Beyond that point, the distance between galaxies becomes so large that even dramatic improvements in speed produce only modest reductions in total journey time. More speculative ideas push further into theoretical physics. One such concept is the photon sail, where a spacecraft is pushed by intense beams of light or lasers. In this system, no onboard fuel is required for acceleration, as external energy sources provide the push. In theory, extremely powerful laser arrays could accelerate small spacecraft to significant fractions of light speed. Another idea involves antimatter propulsion. When matter and antimatter collide, they annihilate each other and release energy with extremely high efficiency. If humanity could produce and store antimatter in sufficient quantities, it would represent one of the most powerful energy sources imaginable for propulsion. However, antimatter is extremely difficult to produce and contain, and current technology is far from practical application. There are also more speculative concepts that go beyond conventional physics, such as warp drives or space-time manipulation. These ideas suggest the possibility of bending space itself rather than moving through it. In theory, If space in front of a spacecraft could be compressed and space behind it expanded, the craft could effectively move across vast distances without locally exceeding the speed of light. While these ideas are mathematically interesting, they require forms of energy or exotic matter that have never been observed or controlled. They remain theoretical and uncertain, but they illustrate the extent to which scientists have considered ways to overcome the limitations of distance. Even if one of these propulsion methods became reality, the challenge of reaching Andromeda would remain immense. The fundamental issue is not only speed, but scale. 2.5 million light-years is so vast that even major breakthroughs in propulsion would still result in journeys lasting thousands or millions of years unless near light speed travel became practical. There is also the question of sustainability. A spacecraft traveling to another galaxy would need to operate for time spans far longer than human civilizations currently exist. It would require systems capable of self-repair, energy regeneration, and possibly even autonomous decision-making across extremely long durations. This moves the problem from engineering into the realm of long-term, artificial intelligence and self-sustaining systems. Another challenge is navigation. Over millions of years, gravitational forces shift the positions of stars and galaxies. A spacecraft launched toward Andromeda would not be aiming at a fixed point in space, but at a moving target shaped by cosmic expansion and galactic motion. Predicting these changes over such long timescales adds another layer of complexity. Despite these obstacles, studying advanced propulsion concepts is not meaningless. It helps define the boundaries of what is physically possible and inspires new approaches to energy, materials, and space exploration. Many technologies that seem impossible at first eventually become real over time, even if they take centuries to develop. Still, when all current and near-future ideas are considered together, the conclusion remains consistent. No known propulsion system can realistically make the journey to Andromeda within any practical time frame. The galaxy remains beyond reach, not because humanity lacks imagination, but because the universe itself operates on scales that are extraordinarily large. As this realization settles in, the role of future engines becomes clearer. They are not tools for reaching Andromeda in a literal sense, but steps toward expanding humanity's reach within its own galaxy. And even that smaller goal represents an enormous and ongoing journey into the unknown. Among the earliest serious ideas for faster space travel, nuclear propulsion stands out as one of the most realistic steps beyond chemical rockets. It does not break the laws of physics, and it relies on energy sources already proven to exist in nature. Because of this, it often appears in discussions about future interstellar missions, including distant targets like the Andromeda Galaxy, even though the gap between possibility and practicality remains enormous. Nuclear propulsion generally refers to using energy released from nuclear reactions to accelerate a spacecraft. Unlike chemical rockets, which depend on molecular bonds breaking and reforming, nuclear reactions release energy from the nucleus of an atom itself. This difference is crucial because the energy stored in atomic nuclei is millions of times greater than that stored in chemical fuels. One of the earliest concepts in this area was nuclear pulse propulsion, sometimes imagined as a spacecraft propelled by a series of controlled nuclear explosions. The idea is simple in principle. Small nuclear detonations occur behind a heavily shielded spacecraft, and each explosion pushes the craft forward. In theory, this could generate extremely high thrust and potentially allow speeds far beyond conventional rockets. Another approach is nuclear thermal propulsion. In this system, a nuclear reactor heats a propellant, such as hydrogen, which is then expelled at high speed to produce thrust. This method is more controlled and has been tested in experimental forms. It offers significant improvements in efficiency compared with chemical rockets especially for missions within the solar system. Even more advanced is nuclear electric propulsion, where a reactor generates electricity that powers ion engines. This combines the long-duration efficiency of ion propulsion with the high energy density of nuclear power. It allows spacecraft to accelerate slowly but continuously over long periods, gradually reaching higher speeds than traditional systems. Despite these improvements, nuclear propulsion still operates far below the speeds needed for intergalactic travel. Even the most optimistic projections place achievable spacecraft velocities at a small fraction of the speed of light. This means that while nuclear propulsion could make travel within the solar system faster and more efficient, it would still be insufficient for reaching nearby stars in short timescales, and completely inadequate for reaching galaxies like Andromeda. To understand why, it helps to return to scale. Andromeda is 2.5 million light-years away. Even if a spacecraft could travel at 1% of the speed of light, which is far beyond current nuclear propulsion capabilities, the journey would still take about 250 million years. This is far longer than the entire existence of most complex life on Earth. This reveals a key limitation. Nuclear propulsion improves efficiency and speed, but it does not fundamentally change the structure of interstellar or intergalactic distances. The universe remains vast, and propulsion improvements only shift the numbers slightly within an already enormous scale. However, nuclear propulsion is still important because it represents a transition point. It is one of the first technologies that could realistically allow sustained exploration beyond Earth's immediate neighborhood. Missions to outer planets, moons of Jupiter and Saturn, and possibly nearby interstellar space become more feasible with such systems. Beyond practical engineering, nuclear propulsion also plays a role in imagination and long-term thinking. It bridges the gap between current technology and more speculative ideas like fusion drives or antimatter engines. Each concept builds on the idea that energy density is the key to faster travel, and nuclear reactions are the first major step beyond chemical energy. Fusion propulsion, often discussed as a successor to nuclear fission systems, offers even greater potential. In fusion reactions, light atomic nuclei combine to form heavier nuclei, releasing vast amounts of energy in the process. This is the same process that powers stars. If controlled fusion could be harnessed in spacecraft, it might allow much higher exhaust velocities and more efficient long-duration acceleration. Even so, the challenge remains unchanged. Reaching Andromeda requires not just faster engines, but fundamentally different relationships with time and distance. Nuclear and fusion propulsion operate within known physics, but they still obey the same speed limits imposed by relativity and energy constraints. There is also a practical issue that becomes more important at higher speeds: shielding. As spacecraft move faster, even microscopic particles in space become dangerous. At nuclear propulsion speeds, this is manageable. At higher fractions of light speed, it becomes increasingly severe. A spacecraft traveling through interstellar or intergalactic space would need protection against radiation, dust, and high-energy particles that could otherwise cause catastrophic damage. Another challenge is long-term reliability. A spacecraft traveling for thousands or millions of years would need systems capable of self-maintenance or complete autonomy. Nuclear reactors would need to operate safely over extremely long periods without human intervention. This introduces engineering problems that extend far beyond propulsion alone. Despite all these limitations, nuclear propulsion remains an important milestone in humanity's relationship with space. It represents a shift from short-range exploration to long-duration thinking. It allows engineers to imagine missions that last decades or centuries, rather than days or months. When viewed in the context of Andromeda, however, nuclear propulsion still feels like a first step in a much longer staircase. It reduces the distance problem slightly, but does not transform it. The galaxy remains far beyond its reach, not because the idea is flawed, but because the scale of the universe is so extreme. As the thought settles, nuclear propulsion becomes less about reaching distant galaxies and more about expanding humanity's immediate horizon. It is a tool for exploring the solar system more deeply, for understanding nearby space more thoroughly, and for preparing the conceptual foundation for future technologies that may one day push even further. In the quiet background of this reflection, Andromeda continues to shine as it always has, distant, ancient, and unchanged by the ambitions of any single civilization drifting beneath it. Among the more elegant ideas for future space travel is a concept that avoids carrying fuel altogether. Instead of launching massive fuel tanks into space, a spacecraft could be pushed by light itself. This idea is known as a laser sail or light sail propulsion, and it represents a very different approach to moving through the universe compared with rockets or nuclear engines. The basic principle is surprisingly simple. Light carries momentum even though it has no mass. When light hits a reflective surface, it exerts a tiny push. This force is extremely small in everyday conditions, but in the vacuum of space, where there is no air resistance, even a small continuous force can gradually accelerate an object to very high speeds. A laser sail spacecraft would use a large, ultra-thin, reflective sail attached to a small payload. On Earth or in orbit, an extremely powerful laser array would aim beams of light at the sail. The photons from the laser would strike the surface and transfer momentum, slowly pushing the spacecraft forward. Since there is no need for onboard fuel, the craft could be made much lighter than traditional rockets. The advantage of this approach is not immediate speed, but sustained acceleration. While chemical rockets provide a short burst of thrust, a laser sail could be pushed continuously for a long period of time, over months or years. This steady push could gradually accelerate a spacecraft to a significant fraction of the speed of light, at least in theory. If such technology became advanced enough, it might allow probes to reach nearby star systems within human lifetimes. Even a small fraction of light speed would dramatically reduce travel times compared with anything currently available. This is why laser sail concepts are often discussed in the context of interstellar exploration, especially for targets within a few dozen light years. However, when the destination shifts to Andromeda, the scale changes completely again. 2.5 million light years is not a distance that can be solved simply by increasing speed. Even if a laser sail could accelerate a spacecraft to 10% of the speed of light, which would already require enormous technological infrastructure, the journey would still take around 25 million years from the perspective of an outside observer. This means that laser sails, despite being one of the most promising ideas for near interstellar travel, still fall far short of intergalactic requirements. The gap between reaching nearby stars and reaching another galaxy is not a gradual extension. It is a dramatic leap in scale. Another important factor in laser sail propulsion is infrastructure. Unlike rockets, which carry their energy with them, laser sail systems require powerful and sustained energy sources located somewhere else, likely in orbit or on a planetary surface. These laser arrays would need to operate continuously for long periods, precisely tracking and focusing energy across vast distances. Maintaining such precision over time introduces another challenge. As the spacecraft moves farther away, the laser beam spreads and weakens. To reach higher speeds, the system must compensate with increasingly large and powerful arrays. This quickly becomes an engineering challenge of planetary or even stellar scale. There is also the issue of deceleration. A laser sail is excellent for accelerating away from a starting point, but slowing down at the destination is much more difficult. Without a second laser system near the target, the spacecraft would simply pass through the destination system at high speed without stopping. For interstellar travel, this is already a major problem. For intergalactic travel, it becomes even more complex, since there is no existing infrastructure in another galaxy to assist with arrival. Despite these challenges, laser sail technology represents an important shift in thinking. It moves away from carrying fuel and instead relies on external energy sources. This allows for much lighter spacecraft and potentially much higher speeds than traditional propulsion methods. In the context of Andromeda, laser sails highlight a key truth. Even the most efficient use of known physics still leads to extremely long travel times when distances become large enough. The galaxy remains far beyond reach, not because we lack clever ideas, but because space itself is extraordinarily vast. There is also a philosophical aspect to this concept. A laser sail spacecraft would be pushed by light for years or decades, gradually building speed as it leaves its home system. In a sense, it would be continuously shaped by energy sent from its origin world, slowly drifting farther into the unknown while still being guided by its birthplace. As distance increases, however, that connection weakens. Eventually, the spacecraft would move so far away that even the laser beam could no longer reach it effectively. At that point, it would continue its journey alone, carried only by the momentum it had already gained. If such a craft were ever aimed toward Andromeda, the first stage of its journey would feel like a carefully controlled push into space. The second stage would become a long, silent drift through interstellar space, and the final stage would stretch into an almost unimaginable passage through intergalactic emptiness, where even stars become rare points of light scattered across darkness. Laser sail technology, while promising, ultimately reinforces the same conclusion reached by all previous propulsion methods. It improves efficiency, increases potential speed, and expands exploration horizons, but it does not overcome the fundamental scale of the universe. Andromeda remains distant, not because humanity lacks imagination or engineering creativity, but because even light-driven systems must still obey the vast structure of space and time. The galaxy continues to shine quietly in the background of every technological dream, unchanged by the limits of any single method of travel.
you.